Okay, let's unpack this. We are doing a deep dive into something called a Bose-Einstein condensate, or BEC. It's a state of matter so bizarre it almost feels like it's from another universe.
It really does. And the idea is, almost a century old now. It started back in 1924 with a paper from Satyendranath Bose, which Albert Einstein then ran with.
And Einstein's prediction was just huge.
So it was profound. He basically said that if you could get atoms cold enough, like just a sliver above absolute zero, they'd stop acting like individual particles. They'd all just collapse into a single quantum state.
The lowest possible energy state.
Exactly. He called it a saturated ideal gas.
Yeah.
And it became this perfect example of macroscopic quantum behavior. It's the bridge between things like superfluid helium and the weirdness of the quantum world.
But our mission for you today is about the monumental, almost impossible challenge of actually making one of these things in a dilute gas. Why was that so hard for so long?
Well, the thing is, for most atoms, it's just thermodynamically forbidden.
Forbidden? What does that mean?
It means that long before they get cold enough to condense, they just crystallize. They turn into a solid. It's like they take an exit ramp before they get to the destination.
So early attempts in the 80s just fizzled out.
Completely. They were using spin-polarized hydrogen, and the atoms were either combining into molecules and getting lost, or they were just sticking to the walls of this super cold container. They couldn't get the temperature low enough.
Okay, so this is where it gets really interesting. The solution wasn't just a small tweak. It required inventing entirely new physics tools.
Two major breakthroughs, really. The first was solving that sticking problem. In 1986, Harold Hess came up with the idea of magnetic trapping.
So holding the atoms in midair with magnets, no walls.
Precisely. And the second was a new way to get them cold enough, which we call evaporative cooling.
Evaporative cooling, that sounds like letting steam off a cup of tea, you're getting rid of the hot stuff.
That's the perfect analogy. You create a magnetic bowl, and you just slightly lower the rim. The very hottest, most energetic atoms literally fly out over the edge.
And the ones left behind are, on average, colder.
Colder, and they rethermalize. You just keep lowering the rim, shaving off the hot ones until what's left is unbelievably cold.
Yeah.
And there's no theoretical limit to how cold you can get, as long as your collisions are right.
So the path to the first BEC with rubidium-87 combined all of this. They pre-cooled the atoms in one trap, then moved them to the magnetic trap. But that magnetic trap had a fatal flaw, a hole in the middle.
Yeah, a 0 point right in the center. And atoms that wandered into it could flip their spin and just poof, they were gone.
Yeah.
Leak out of the trap.
How did they fix that?
With a brilliant piece of engineering called the top P trap, the time-orbiting potential trap. They used a small, rotating magnetic field to literally stir that 0 point around, moving it so fast the atoms couldn't follow it. It plugged the hole.
And that was it. That worked.
That was it.
Yeah.
And the proof was incredible. When they switched off the trap, the regular hot gas expanded in a perfect circle. But the condensate, this single quantum wave,
It expanded in an ellipse matching the shape of the trap. That was the smoking gun.
it was the dead giveaway. Proof of quantum mechanics you could see with the camera. And the experiments that followed were key. They measured how the condensate decayed and found the three-body recombination rate was way, way lower than for a normal gas.
Because it was a single coherent thing, not a jumble of individual particles.
That's it. There were fewer density fluctuations. It was behaving as one.
Okay, but let's talk about one of the most wild results. The bossa nova. What on earth was that?
Right, so using a technique called Feshbach resonances, they found they could use a magnetic field to basically dial a force between the atoms. They could make them repel or attract.
And they dialed it to attract.
They did. And the whole condensate just became unstable. It collapsed on itself and then violently exploded. It looked so much like a tiny supernova that they had to call it a bossa nova.
Wow. So what's the big takeaway for you listening to this? It seems like the core problem wasn't just temperature.
Not at all. The real hurdle, the one all this technology is built to solve, was collisions. You need the right kind of collisions.
What do you mean right kind?
You need lots of good, elastic, billiard ball-like collisions to make evaporative cooling work. And you need to avoid the bad, inelastic collisions where atoms stick together and get lost from the trap.
So the magic number is something like 100 good collisions for every bad one.
Roughly, yeah.
What?
About 100 elastic collisions per atom over the lifetime of the trap. And that leads to the final thought I want to leave you with. Now that we know this technique works for many different atoms, the game has changed.
It's no longer a technology problem, it's a physics problem.
Exactly. The question now is, How many new elements or even molecules are out there that have the right properties? How many more species could we push into this bizarre quantum state just by finding the ones with that magic collision ratio?